Hello, and welcome to Linear Systems and Signals. This is course number ECE 345 at Rutgers University, and this is the video lectures developed for the fall 2022 semester. If you're taking this class, hello again. My name is Anand Sarwate. I'm an associate professor in the Electrical and Computer Engineering department here at Rutgers. And if you're watching from outside, hello to you as well. This course and this video playlist will be evolving over time, containing videos recorded over the last 3 years for this course. And so I'd like to kick off things by sort of giving an introduction to what this class is really about. What do we mean by linear systems and signals? So let's take a look. So first off, the question is like, what is a signal and what is a system? I mean, linear, maybe you've got some idea of what linear is because you're, taking linear algebra, or maybe at least you know what a linear function is. It's line, linear, line, makes sense. But what makes a system linear, and what is a system anyway? And what is a signal, and how does that relate to a system? So we're going to use a pretty abstract definition here. And I want to use this abstract definition because I want to emphasize that what this class gives you is a different perspective on how to look at things, on how to look at the world and how to think about information flows and so on. So in that suitably abstract way, we'll try to make some concrete examples. A signal is a measurement of a quantity measured over time or space. That seems pretty vague. Measurement of a quantity over time and or space. So, we're actually, this is somewhat restrictive. I shouldn't have to say time or space. I mean, it could be over something else, but really to think of it as a voltage wave over time, for example, that is an example of a signal. But still, it's kind of pretty vague stated this way. And then systems is no better. We say a system is something that transforms one signal, which we call the input, into another, which is the output. So a system has an in and has an out, and essentially it's like a box with a wire going in and a wire going out. Sometimes they're not even wires, like with a wireless system, like in a communication system. So this is not any less vague, right? And actually, that's kind of the beauty of this whole area, is that this is a way of thinking about engineering design and about system design, technology design, in terms of essentially boxes and arrows. And we'll get to that in a few minutes. So one major theme of this class is that signals are, in fact, everywhere. And once you start noticing them, you'll start seeing them everywhere. So this is kind of an exercise for yourself to build up over the course of this semester, is to build up your ability to notice where the signals are. You can always look at something and say, I wonder if there's a signal in there. Yeah, I think there actually is a signal. So let's give some examples of what are examples of signals, signals that we may in fact encounter during this course. One is signals that come from wireless communications. Your phone right here, is got some antennas in it. It's got Bluetooth sometimes and has a cellular connection up to your cell tower. Those are antennas, and there's wireless. There's electromagnetic waves coming off of those. Those electromagnetic waves are signals. There's also signals inside, where components of the phone are talking to each other. Sending little messages to each other internally. Those are also signals. If you think about sort of other wireless phenomena, radio signals, all sorts of radio astronomy and so on, those are using signals. Radio astronomy is using signals, sending them out, getting them back. Radar also uses signals all the time. It's sending out pulses and receiving returns, and then trying to compute locations of things. Of course, if you've taken the prerequisite course for this course, is a course in RLC circuits. Basically, you'll have seen many signals that you see in lab, coming off of a function generator. You're measuring the voltage across a resistor or something like that, or the output of the terminal port of a circuit. So all sorts of electrical signals are, of course, signals. Then, of course, we have things like, audio signals. We even have temperature signals. You can have like a sensor, which is a temperature sensor. It's reading, say, the temperature in this room. And it's reporting it back to perhaps some central controller, which controls the HVAC system, the heating and cooling system in the building. So this is another example of a signal. It's measuring a quantity over time. It's measuring the temperature over time. And same with a microphone is measuring the sound pressure waves coming into it over time. And finally, images and video, in fact, are also, you can think of these as signals. And so there's an image processing is a whole field, and video processing is a whole field, and designing image compression algorithms and vision compression algorithms, basically all the codecs that you see used in these applications, those are all also processing signals. These signals are measurements of essentially light intensity on a sensor over space, right? And also time if it's a video. So when I did the pre-course survey, I've done this several times this year and in previous years, I've gotten a lot of interesting examples of signals from students about things that they might be interested in. And so a lot of people, of course, based on classes you've taken before, have talked about circuits and other sorts of things, looking at function generator outputs. Many people identify EM waves of various types as being signals, AM radio, terrestrial radio, TV, Wi-Fi, Bluetooth, all of these different technologies that send out electromagnetic waves and receive electromagnetic waves to do communication. Those are also, using signals. Some people identified multimedia, as I mentioned before, sounds, images, and video. Other people talked about more like applications. They're like, oh, signals are things that happen in communication systems, or signals that happen in music or audio processing systems. Or a lot of people talk about event detection. And essentially, like the signal is like, like an earthquake. You detect an earthquake, and that triggers a reaction, an alarm. So the signal, some people identify the signal as the alarm. I would actually say the signal is this seismic signal that's being measured by the sensor that's measuring the earth tremors. And some people went straight to the abstraction, went straight to the math, and said, oh, yes, signals are like sines and cosine waves. And that's true. We can also think about signals, but really what we should think of is we're modeling signals. We're modeling the real world phenomenon. That is the measurement that's being taken over time. We're modeling that using mathematics, using a sine or a cosine wave. So we're going to be doing a lot of math in this class, but the math is a model for some real world phenomenon. It's always connected back to some real world phenomenon that we're trying to understand better by modeling it using mathematics. So the different types of signals people identified, and we're not going to be talking about these directly in class, but they do have the word signal in them. And in some way, you could try to figure out where is the signal. I think the interesting exercise is to say, where is the signal in these things? So people talked about codes. Some people talk about cryptography. And so it's like, secret signaling. You're trying to send a secret using a signal. So it's an aspect of the signal that somehow you have done something, used a signal to encode some information. So that is using a signal. The code itself might not be the signal, but the encoded message might be the signal, or might be translated into a signal that you can then send. A lot of people talked about car-related things, traffic signals and turn signals and so on. And these are signals because they are sending they're communication systems of a type, right? When the light turns red, it's a communication system sending a message to you to stop. And it's sending that by sending a very simple, if you can think about it, it's sending like a very simple, pulse, if you like. You could say red is 1, yellow is 0, and green is -1 or something like that. You can imagine modeling it like a little bit of a kind of a square wave. And then you would have a signal. You would say, oh, that's actually the input that's coming into the electronics in the traffic light. People talked also about traffic control. And indeed, you can get signals. You may be measuring things about the traffic, and then you might be then doing something with that signal that you've measured from the traffic, and then applying some, feedback via another signal to try and control the traffic lights. The lights themselves, the point is the lights themselves aren't necessarily the signal. The signal is what's happening to control the lights, and what you're getting, what you're measuring is actually coming from some sensors, maybe in the roadbed or something. Finally, some people mentioned emoji, which are signaling systems of some kind. You're sending a message. But again, this is, I think, what people are catching on to is that signals are used in communication, and we're going to use a lot of communication examples in this class. partly because that's my background is in a bit in communications. So it's something I know a little bit more about. But you can also think about how might I represent, say, mathematically, a sequence of emoji. And if you can do that, then maybe you found a signal in there. So signals in general, as I said, are mathematical functions. We're going to model them. We're going to treat them like they're mathematical functions. So we have like voltage level over time, V of t, right? So that's a function V of t. Voltage at a particular point, you're measuring it at a particular point in the circuit over time. I talked about pressure sensors along the road. Those are actually being measured over space. So you might have a long stretch of road, you have a bunch of pressure sensors, and you're measuring how the pressure is varying over time. This might give you a sense of how fast the traffic is moving. For imaging systems, the pixel intensity is, there are these, some cameras have these charge coupled devices. So it's basically measuring the charge that's accumulating on a surface from the photons hitting the surface. So this pixel intensity is on a video camera, for example, sensor is being measured over space and time. Space because it's measuring a particular image area, and then time because it's taking many images over time. So we're going to focus mostly on 1D signals. There may be some assignments where we talk about 2D signals, maybe not so much video or 3D signals, but some 2D stuff. But we're really going to focus on one-dimensional stuff because once you build the intuition for how one-dimensional signals and systems work, the two-dimensional thing is not a big a leap. So we want to make things kind of consistent and easy. I talked about space and time. So we're actually just going to think about everything as a function of time, with the understanding that if we were in an application talking about road pressure sensors, we might be talking about it over space. We're going to, and then we'll call the dependent variable the measurement. And so that measurement, of course, might have different units. If it's voltage, it's one thing. If it's sound pressure, it's another thing. They're different units. This is, when we think about the physics of it. But really, we're just going to be thinking of a mathematical function, say x of t, which measures the quantity x at time t. So we have different ways then of thinking about actually what a signal is, right? So we have a modeling of it. We have an analytical form of it. So we could say that x of t is cosine 120 pi t. That's a sine wave at 60 hertz or cosine wave at 60 hertz. I could also look at it graphically. Whenever you look at a signal, one thing you should try to do, and it really helps a lot, is to try and picture what it looks like. And if you don't know what it looks like, open up MATLAB and plot it, or open up your favorite program and plot it. And take a look, build an intuition, build a feeling for when you look at a function, what does it look like? Because that gives you a lot of help in trying to understand what's going on in the system, more help than I think just the symbols, manipulating the symbols around are going to help you, right? You have to you'll get a kind of more physical feeling about what's going on. And then the third way we look at signals, especially in this class, is computationally. We're going to be doing a lot of simulation. We're not going to be building a lot of hardware. So sorry for the folks who wrote in their pre-class survey that they really wanted to do a lot of hardware. That's not this course, unfortunately. We're going to be doing a lot of simulation, though, and based on the simulation, then you could try to ask the question, how do I build the hardware that would create the system that I can successfully emulate on the computer? And this is important because in almost every system that we design nowadays, we do a lot of design on computer first, and then we build it. So we have to be able to understand how to simulate the system that we want and make sure that at least in simulation, it works correctly before we decide to invest the money to build it. So always keep an example or a few examples in your mind to make things more concrete. You're going to see an abstract definition of power. But if you think to yourself, okay, well, voltage, I think about like one of your examples might be like, I'm just going to think about the voltage on a wire, that I measured in class that one time. Then it's like, okay, what is the power? Oh, it's, V squared over R. Okay, so that's why that formula looks like it's kind of doing V squared over R. So then you'll get to see why it is that we measure energy and power in these ways when you have these sort of concrete examples of signals. You might have might be an audio signal, for example. So for each new idea or concept that we encounter in this class, my challenge to you is to ask yourself, I'm going to show you probably what it looks like as a formula. I'll probably also try and show you what it looks like as a picture. And you're going to do in assignments what it looks like in code, but you have to be able to interchange your way in between these things. So if you see a formula, one thing, some of you might be kind of more programming oriented. And if you see a formula, like x of t equals cosine 120 pi t, then you should say, oh, well, how would I code that up? And then try and code it up. And then you can produce this block. And this will create this three-way conversation between these different ways of thinking about signals that'll be really productive and really help you understand better what we're doing in this class. So the second theme of this course is that systems, of course, are also everywhere. We can't just have signals everywhere. Systems are also everywhere. And again, once you start noticing different things, you say, okay, what system is that? What is it doing? What is it? It's translating an input signal into an output signal. How is it doing that? So a system is something that transforms one signal into another. So we can think about, since you've seen a lot of systems already, you just might not think of them as systems. So if I look at a stereo equalizer or like a mixer board for audio, I can raise and lower different frequencies. So I can turn the bass down, I can turn the treble up. This is a system which is going to take the input audio signal and then produce an output audio signal. If I push the bass down, it's going to have an output signal with less bass. If I push the bass up, it's going to be pumping the bass. So this is a different, this is one type of system. It translates the input audio signal into the output audio signal. Any communication system is involving signals because it's sending a message from one from a transmitter to a receiver, or maybe to multiple receivers. And this information, this message is being encoded or turned into an electromagnetic wave, which is a signal. So your phone is connected to a Wi-Fi router, say in the classroom or at home or wherever. Then your phone is sending electromagnetic waves. They're sending signals, and they're sending signals back and forth to each other, right? And this is what's happening at what we call the physical layer of the communication system, right? At the lowest level, whatever. We're really talking about what are the waves that are being sent. It's not just electrical engineering type systems, right? The brain is also a system, or the brain has lots of systems in it, and we can actually think about a single neuron as a system. We can think about or we can think about parts of the body as being systems that take sensations and turn them into neural impulses that go to our brain. People also work on what are called cellular communication systems, but not like cell phones, but they talk about like how do cells communicate with each other through chemical signaling. And so they're again talking about signals. Those signals are measurements. What are the measurements? They're like the concentration of certain chemicals outside the cell membrane. So in the human eye, we can think of the retina and the ganglia, which are sitting right behind the retina, are translating the light intensity that's hitting your eyeball onto the optic nerve, and so it's turning it into neural spikes. And actually, we'll see an example of this in one of the problems that we do in class. Finally, there's a whole area that this class, I've talked a lot about communications, I've talked a little bit about signal processing, but there's this whole area of control systems. And control systems also uses lots of signals. Here you want to say control the position of a robot arm. You are going to be translating whatever you're sending the servo, you're going to send the servo motor, a signal. It's going to send it a signal and it's going to move the arm. So the input is the signal you send to the servo motor, and the output might be the position of the robot arm. So some examples that people gave in the pre-class survey and in previous years are, of course, coming from these applications, communications in DSP, from circuit design, mechanical systems. People talk a bit about appliances, and appliances some appliances are like very obviously kind of systems. You can identify the input signal and identify the output signal. Many appliances and most technologies are made up of many systems. And so what's interesting to do is to try and identify, well, what kinds of systems inside this bigger piece of technology must there be in order to make that technology work. But for our purposes in the class, from an analytical point of view, to try and understand the modeling, to try and help us learn how to design systems and analyze systems, we're going to be thinking of a system as a function which takes inputs to outputs and essentially some sort of equation that relates the input signal to the output signal. And other systems that we're not going to be talking about in this class are things like operating systems. Again, like the word system is very used in lots of different contexts. So we're in this class, we're meaning a very specific thing when we talk about a system. We're not going to talk about operating systems. We're not going to be talking about the solar system or really the bus system. Although these are all examples of systems. We're the word system, but it's not the kind of system we're going to be studying in this class, the kind of system that is amenable to the kind of tools that we're going to be learning in this class. So as I mentioned before, we can think about signals and systems as being like sort of a boxes and arrows sort of view of things. So in robotic control, you have a voltage signal going into the servo, controlling the robot arm position. In acoustics, you have a sound pressure wave going into your ear, and turning into a set of on your auditory nerve, getting some spikes coming. Your neurons are firing, going into your ear, even as you hear right now when you're hearing me talk. And similar, and also like say satellite communication, you send an electromagnetic wave up to a satellite. The system, you can think of it as like the Earth's atmosphere is going to distort. It's going to do something to that input signal. What you receive at the satellite is not exactly what you send. It's something different. That thing is distorted, messed up a little bit by the system that is sitting either implicitly between in between the two. We call this the communication channel. So in abstract, we can think about a system as just a box. We'll often use the letter H for it. And say you can think of, if you're thinking about voltage, you could have a V in coming in and a V out coming out. And if you plug in a circuit in there, you can plug in a V in and a V out, in place of that H. And so you can see those circuits are also systems, right? So all of these systems that I gave before can be thought of in this way. And in particular, one thing I want to point out is that any measurement device, anytime you measure anything, remember you're creating a measurement over time. So that thing, that sensor, is creating a signal. And what is it creating a signal out of? It's creating it out of some maybe natural signal that exists that you don't have access to. So for example, I would like to really know what is, I'd like to have a microphone which like really can tell what are all the sound waves going on in this room. But the microphone actually is frequency selective. It is designed to do better at picking up some frequencies and not better, in particular, it's better at picking up frequencies around the human voice range and not good at picking up frequencies like super high frequencies like that dogs can hear. And so this selectivity means that this microphone that's sitting next to my face is itself a system that's translating the sound pressure waves from my mouth into an electrical pulse that's going into my headphones and then into the computer. So a signals and systems worldview then, right, is one where you try to look all the time for what are the signals, where are the signals, and where are the systems. We're going to model very complex technologies in terms of these sort of boxes and arrows. It's made up of many systems. And then what we're going to try and do in this class is pull out some of those systems, try and understand how they work, and understand what concepts are needed to make all these individual components work. In later on follow-on classes, you can start once you have this kind of understanding of how the individual components work, you can start putting them together and try to understand when they're easily put together and when you need to account for some other issues that arise in engineering design. So fundamentally, this is like a block diagram view of engineering. Instead of thinking about individual circuit components, we're going to think about something more abstract like this box, which is a system, which represents the transfer function of the input to the output. Arrows are then things that carry signals, and that could be a wire. So they look like wires because they're drawing a straight line. The arrow looks like a wire, but it could also be the air, sending satellite communication. It's the air and the atmosphere. It could also be water. There's underwater acoustic communication systems. That's how say whales talk to each other, but it's also how you communicate in submarines, for example. And then systems are boxes. Systems are boxes that transform one signal into another signal. They take an arrow, input signal, put an output arrow, output signal. And so the point is, the big takeaway is that these are the building blocks that let us understand more complex technologies. The reason for doing this is that you can then talk about chaining systems together. And in fact, that's really one of the big contributions of this kind of linear system theory, is that we can then say, if a system is one that translates a signal to another signal, then I can start plugging these things into each other, like Legos. And so, for example, if I think about the microphone, if I'm say giving a talk with a wireless microphone, the sound waves are going into the microphone, or maybe you think about your Bluetooth you have Bluetooth headphones. The sound wave goes into the microphone in the mic. It gets turned into a voltage signal. It then gets translated into wireless. If you're doing Bluetooth, it's being translated into a wireless electromagnetic wave that's going from the Bluetooth to say a receiver, and that receiver could be in your phone, or it could be on a speaker if you're talking over a speaker system. It's going, let's say going to a speaker, it's going to an amplifier then, and then the amplifier is going to take that voltage and amplify it and send it to a speaker, and the speaker is going to then produce more sound waves, and those sound waves are going to go into your ear, and then from your ear it's going to get turned into neural impulses that are going to get sent to your brain, and then there's again more systems. So we're always translating systems, translating signals with systems all the time, and we're doing it through multiple systems, and we're trying to identify what are the properties of these individual boxes that let us understand what happens, how is the sound wave that went into this microphone related to the sound wave that comes out of the speaker. They're not necessarily the same. There might be some feedback, it might be distorted, all sorts of things. All that's going to happen because of issues that arise in this block diagram. So if you want to see a particular example of a technology like this, we can look at something like acoustic echo cancellation. So if you have echo cancellation in your headphones, which I'm sure you do in many of you, you have a whole way of modeling this entire system using this kind of boxes and arrows mentality, right? So we have an X of N signal coming in, it goes into a speaker, the speaker is going through a system which models the room acoustics. That creates echoes. And then there's this, in this particular block diagram, they're talking about some double talk and extra noise. That goes into a microphone. That microphone input goes into an adder, and what you're trying to do is build this adaptive filter, which is going to cancel out the X part. It's going to cancel out what are the echoes. It's trying to learn this adaptive filter, W hat, is trying to match the room acoustics in order to cancel out the effect of the room acoustics. So this is how adaptive acoustic echo cancellation can work. And so there's a nice paper, I can citation here, you can look it up. And so this point is that you can do really cool things using exactly the kind of methodology and ideas that we're discussing in this, we'll be learning in this class. So in addition to different ways of looking at signals, we have different ways of looking at systems. We can also think about systems in this class, we need to think about them as mathematical objects, that are relationships between input and output signals. We're going to talk about the input-output relation that defines the system. But we can also think about it in terms of implementation. We could say, like, how do I build this system, right? And so if I wanted to make a simple low-pass filter, I have this RLC circuit. I think it implements a low-pass filter. And then, you could then say, well, how do I build it, right? And then you could say, well, okay, but how can I simulate it in code first? Because maybe you want to build a much more complicated circuit than this. This is just one piece of the whole system that you end up wanting to design. The goal in the end is to create these modular and reusable elements, these boxes that we can think of them really as boxes that we can just kind of plug into each other. So that's what allows us to build up complex functionality from simpler building blocks. Instead of having, you might have like 10 boxes in a system, right? 10 boxes in overall technology with different systems, like in the previous slide. And to say, oh, I need to figure out all the resistors and all the capacitors and all the inductors and all the op amps that are going to go into that system holistically, that technology holistically is going to be, it's a tall order. If you can isolate and design each component separately and then be guaranteed or have some guarantees about how easy it is to plug them in together, you can get a lot farther, a lot faster. So the point really is that all of this math that we're going to be doing, and it's going to be a lot of math, is math that matters. It's math with a purpose, right? And we're not just doing math for math's sake, although some people might like doing math for math's sake. I am a person who likes doing math for math's sake, but it's not the point of this class. The point of this class is do math that matters. And developing the right mathematical language to talk about signals and systems is really important, because what it does is it gives us these two properties that I talked about. Right? One is generalization, right? One is that if you might have a system which you write abstractly mathematically, but it might actually be the same or very similar model for many different applications. That is, when you talk about making a low-pass filter, right? You talk about, well, how do I make a low-pass filter? You could be applying that low-pass filter to a communication system. You could be applying it to time series data from finance. You could be applying it to a control signal. You could be applying it to all sorts of things. So, but what you're doing is trying to figure out, how do I design low-pass filters? Not how do I design this one thing for the communication system only? right? And so this is what the mathematical abstraction lets you do. It lets you understand what is the process, what are the trade-offs in designing low-pass filters. Then you can figure out what is the best one for your particular application. Secondly is this thing that I mentioned a lot now, composition. Being able to chain together boxes and arrows together and analyze these sort of multi-step systems through understanding the single individual steps. And finally, as I've said earlier in this presentation, analysis lets us design before we build. And designing before you build, thinking twice, measuring twice, cutting once, as they say in sewing, or in costume design, so on. You want to design before you build. Having a little trouble with my slides here. Okay, so what's next, right? So what's coming up in the class, and this is the wrapping up this presentation. Okay. So as a rough outline of the topics, there's 6 units that we're going to go through. We're going to talk about signals and systems, basics of signals and systems. Then we're going to drill in and zoom in on what are called linear time invariant systems. These are a special class of systems which have a very nice story and a nice way of analyzing them, and they're very easy. They're very not easy. They're very nice to work with because they compose well and they have a lot of nice properties. They have a kind of a beautiful story associated with them, and they're very useful, incredibly useful. And so we're going to focus on, first, we're going to work on some continuous time stuff. So we're going to look at analog signals and continuous time system design and continuous time signal processing using Laplace transforms and something called the Fourier transform. And then we'll switch over to the discrete side of the story when I think about discrete time slotted systems. Like for DSP, we'll talk about Z transforms and the discrete time Fourier transform. So engineering design, you should think about it is this kind of cycle, right? You want to first, you're faced with a problem. You want to design technology for a particular application. First, you need to model and understand what are the signals and systems and constraints that are operating that system. And constraints could be you have limited power budget, you have limited speed. In circuit design, constraints could be like footprint on say a larger chip. Your system can only occupy a certain footprint. You want to understand all of these constraints and what do they say about the mathematical model and what you're trying to optimize. Then you can try and design. You can try and say, oh, okay, how do I optimize my performance, whatever my performance metric is, subject to these constraints? So how do I design the right signals and design the right systems so that satisfy the constraints that will make a solution? At least it works, on paper, for example. And then you want to simulate and then potentially build your system to see if it does work. And sometimes it won't work, right, in practice, because your model was wrong. Your model was too simple. You forgot something, right? Especially if you're simulating, this is great because you can go back and you can say, okay, I need to fix my model. What can I do to fix my model? How can I make it more realistic? This is a going, and you're not going back totally to the drawing board initially. You're going back and figuring out what did you miss? What did you miss? And you're going through this cycle. And this is the same way you do. This is the same way you do problem solving. You think you know how to do it. You work on it. Seems like it's going to work. It doesn't seem to quite give you the solution. Then you go back and say, well, what did I miss? Same thing with engineering. This is exactly what you're doing in engineering. We're going to see a nice example of this later in the semester, or hopefully some nice examples of this later in the semester. So this class is about building the foundations for doing this cycle, this modeling and analysis, and this design and simulation. So as we go forward, please remember the following takeaways, at least, right? Signals are everywhere. Signals are everywhere. Look for them, try and find them. Systems are everywhere. What do they do? What are the systems doing? What signals are they? What is the input? What is the output? What are they trying to do? And the goal really is to, again, understand these building blocks, the building blocks of more complex technologies. I can't sit here and tell you, like, here's a whole communication system. And like, I can tell you exactly how every single little piece works because there's like too many pieces in a communication system. I can tell you how certain pieces of it work. And later on, when you study communications, you can try and see how those things fit together better. And finally, really that mathematical modeling is really the foundation. It is the language that will let us unlock the potential of this way of thinking about system design and engineering systems. So I look forward to the rest of the class, and keep tuned. For those following along on the video lectures outside of Rutgers, it'll be a little bit more on the technical side, and for those who are in class, we'll see a lot more examples in the class during our class sessions. Okay, take care.